In section 3.3, determinants and inverses, we're going to finally make the connection between determinants and one of the most important application of determinants, and that's inverses of matrices. Before we get started with the section, I want to remind you of some notation from section 3.1 that we covered a bit earlier, and that's this notation for the cofactor Cij corresponding to the element Aij of a matrix A. So if you don't remember what a cofactor is, now would be a good time to go back and look at your notes or a previous video to remind yourself of what those are. Now let's look at a new definition. Let A be some square matrix. In this case, it's going to be n by n. And we're going to define the following two new matrices. Here's the first one. This is known as the matrix of cofactors. And what we've done is we've taken each of the cofactors of the matrix A and built a matrix out of cofactors. So to compute each of these entries of this new matrix, the matrix of cofactors, you have to compute all of these determinants. Remember, a cofactor is a positive or a negative of a determinant corresponding to this entry. And the other new matrix that we're going to define here is called the adjoint of A. And then there's a notation for this. AdJ for adjoint is used as a function with A plugged to n. And you should notice that the adjoint and the matrix of cofactors are very similar to each other. But the adjoint of A is actually the transpose of the matrix of cofactors. So we've swapped out the columns for rows. So now we'll get to the theorem that tells us why the adjoint is important. Let A be some square matrix where the determinant of A is not zero. Then this theorem tells us that A is invertible and A inverse is actually equal to 1 over the determinant of A times the adjoint of A. We won't be proving this theorem in the video. If you're interested in the proof, it is in your textbook, and it is pretty technical. But if you'd like to read it, it's there. This formula, though, is extremely important, at least on a theoretical basis, because if we know the determinant of A is not zero, then we actually have a formula that we can just plug the matrix into to get an inverse. So what we want to do to get our hands on this formula, or get a grasp of this formula, is to use the theorem to find the inverse of this 3 by 3 matrix. So the first thing that we have to do is double check that the conditions of the theorem are satisfied. So do we have a square matrix? And that's easy to see. This is a 3 by 3. And the other condition is that the determinant is non-zero. So we have to check that by computing the determinant of this 3 by 3 matrix. And I'm going to use the strategy that we learned in the previous section using row reduction, a Gauss-Jordan elimination. So what we want to do is start with the matrix and end up on our last step with a upper triangular matrix. So the first thing I'm going to do is use this one here to eliminate this one. So I take row 3 and I subtract row 2. And here's what we get for our new row 3. So we create a 0 here and then we get 2 and 3 as the remaining entries. Since we want to end up with an upper triangular matrix, we need to put something non-zero here, if we can. So I take this 1, and I want to move it here by swapping rows 2 and 3. So before I move on to that next step, I do want to point out that we're computing the determinant, and when we add or subtract a multiple of one row from another, it doesn't change the determinant. So that's why there's an equal sign here. But when we swap rows, when we interchange rows, we actually get a minus sign. So when I change row 1 and row 2, I actually have a negative of the original determinant. So we pick up a minus sign here, and here's our new matrix. And in order to create a upper triangular matrix here, I'll have to get rid of this 2. And the way to do that is to use row 2, because there's a 0 here. When we add a multiple or subtract a multiple from row 3, we won't change this 0. So I want to use this 3 to eliminate the 2 in this entry. So we'll take row 3 and subtract off 2/3 of row 2. And since we're adding or subtracting a multiple of one row from another, we get an equal sign, and we don't pick up another minus sign. We just copy this one down for our determinant. And now we do have an upper triangular matrix. We've created a 0 down here, and then the bottom right entry of our 3x3 matrix is 1. And since we have an upper triangular matrix at this step, we know from the last section that the determinant of this upper triangular is just the product of the diagonal entries. So that's what we'll do to finish off the determinant. We have a minus sign, and then 1 times 3 times 1. So overall, we get a minus 3 for our determinant. Okay. So after doing that work, we know for sure that the theorem applies because we're looking at a square matrix whose determinant is minus 3, which is not 0. Okay, so the next thing to do is to work towards computing the adjoint of A. And in order to do that, there's lots of work that we have to do. We have to compute the 9 cofactors of our 3x3 matrix. So just start on the upper left side, the upper left entry of our matrix, and compute C11. And I'll show you the details on a few of these. For C11, we need to cross off the first row and the first column. So the determinant that we're computing is a 2x2 down here in the bottom right. And since this is the upper left entry of our original 3x3 matrix, we get a plus sign. So you do this 2x2 determinant, and remember to do that, you multiply the diagonals crosswise, and then take the difference. So in this case, you have 12 minus 12, and you get 0. Okay. And then let's talk about a couple more, maybe. C12, we pick up a minus sign since it's the 1, 2 entry. You might remember the formula for the cofactor. It has minus 1 to the 1 plus 2 in it. So minus 1 cubed gives us a minus sign. And then we have to figure out the 2x2 determinant that corresponds to the 1, 2 entry. So you cross off the first row and the first column, and then what remains is this 1, 1 and the 3, 6. So you make a little 2x2 matrix out of that and compute its determinant. So that's 1 times 6 minus 1 times 3. So that gives you a 3 from the determinant, and the extra minus sign gives you negative 3. Okay, so I think that's the last one that I want to talk through, but I'll give you a moment to look at all of these. before we move on. So I've computed all of the determinants, all of the cofactors, and you should try doing these on your own as well, because you'll need to do this sort of thing on your homework. Okay, so after you've spent a few minutes computing all of those cofactors, you have to move on to finding the adjoint. So let's think back to what the adjoint is. Here's the definition again. So it's the matrix of cofactors, so the cofactors in their normal positions, and then we've taken a transpose. So you can see the pattern here. This is the normal pattern C12, C11, C12, and then just the corresponding cofactors. And then we swap rows for columns. So the way I've organized my computation here is that everything is in its usual position in the matrix. There's sort of a matrix of computations here. So what we're going to do is swap our rows into columns to get the adjoint. So 0, minus 3, 2 will go in the first column, minus 6, minus 3, 3 will go in the second column, and then 3, 3, minus 3 will go in the third column of our adjoint. And here I've written that out. Let's pause there for a second. And then our last step is to actually compute the inverse using the formula from the theorem, which I've written out here again. A inverse is 1 over the determinant of A times the adjoint of A. And we've already computed the determinant and the adjoint, so we just have to plug in the 1/3 in the denominator, and then we can look up here at the adjoint matrix. So we just divide each entry of the adjoint of A by minus 3, and then we get this new matrix here. So that's how you compute an inverse using the theorem that we just learned and the adjoint of a matrix. So what you probably noticed is that there was a lot of work, and it might have even seemed like more work than just computing the matrix of the inverse like we did way back in chapter 2. And that's because it is actually more work. The importance of this theorem isn't so much the formula that we want to use, or we don't want to use it as a formula for computing the inverse. It's often used on a more theoretical basis. So just having a formula for an inverse, even if we never plug things into the formula, can be extremely useful. And in the next video, we're going to see a little bit of that.